Hello there. Today we've got another classic problem for you. And this one is a combination of astronomy, physics, and geometry. You know, that's what makes this so great. It's just totally amazing problem. And I got something special. This, okay, might help me get my act together. Hang on a sec. Since this is kind of a big problem, let's see if the coffee helps. All right, we're going to do a problem called the points of attraction. Points of attraction. Except we're going to do a complete job, you know, like a much more thorough, better job than what you see somewhere else. So what is all this about? We have the Earth and the Moon. Okay. And there's got to be some point, probably closer to the Moon, where if you put a mass m, the force due to the Moon, attraction, you know, between mass m and the Moon, and the force between the Earth and mass m are equal. Okay, so this is a point of attraction. Now, a little bit of reflection makes you realize that there must be another such point here where the two forces are equal but in the same direction. And a little bit more reflection and you start to realize, hey, there must be points. There must be points all along some kind of curve here where the forces, well, the forces may not be in the same direction, but they can be the same strength, yes? And we're going to call this the curve of attraction. Now I'm going to do something that you don't always see when you see this problem done, and that's this. We're going to prove that the curve of attraction is actually a circle. So the curve of attraction, we're going to prove this, is a circle, and we have to find its center and radius, and then we're going to draw all of this. Okay, so this is what we want to prove. We want to prove that this is true. It's not an ellipse, it's not a parabola, it's not something like that. It's got to come all the way around because you have another point here. So it has to be either a circle or ellipse or something like that. And we're going to prove it's a circle. All right, so let's begin. The forces are equal at the point of attraction. Now, Newton's law of gravity gives us something like this. Well, this is going to be r squared, and this here, gm m moon, little r squared. What do I mean by that? Okay, let's draw some geometry here. Take a point, mass m. Here's the Moon, and here's the Earth. So this small distance is little r, and this big distance is big R. We're going to take the origin to be over here. Okay, now let's introduce some geometry. We'll call this distance x from here to here, and the whole distance from Earth to Moon, we'll call that d. And in this case, this piece here is d minus x from here to here. Okay, great. So this is our reference drawing. We'll come back to this. Now, here, okay, force due to the Earth, mass of the Earth times mass of particle times r divided by r squared. Same here, except force here is computed by dividing by this distance squared. Luckily, a lot of things cancel out, and I end up with this nice little formula like this. Mass of Earth over mass of Moon is r squared over little r squared. Very, very beautiful formula. Okay, let's work on that. All right, what is the mass of the Earth? What is the mass of the Earth? The mass of the Earth is approximately 6 times 10 to the 21 tons. And the mass of the Moon is just about 7.35 times 10 to the 19 metric tons. Okay. Let's divide these. We'll make a dimensionless factor mu, Greek letter, me over m moon. That is approximately 81.6. So the Earth is 81.6 times more massive than the Moon. That is a useful number to know. You never know when you're going to need that in a competition or something like that, so I recommend you memorize it. It is not hard to remember. It might be hard to remember these, but not hard to remember that. Okay, so we can introduce mu here. So we have mu equals me over m moon is big R squared over little r squared. We end up with big R squared is mu little r squared. Now, I want to take a moment, okay, get this, and think about it, okay? Sit back, think about this. A beautiful equation. This equation encapsulates the entire problem, all of the ideas of our problem, all of our astronomy, all of our physics, all of our geometry is all encapsulated into this beautiful equation. Okay, the essence of the whole thing is in this equation. Very amazing, very beautiful. All right, to prove that this curve here is a circle, I need to introduce Cartesian coordinates. We have x, but we need y now, so this is our y. Now, I apply Pythagoras law. X squared plus y squared is big R, and likewise this squared plus y squared is little r. So I can use Pythagoras law and expand this. X squared plus y squared is mu. Now, let's be careful with algebra. D minus x squared plus y squared. Okay, this is mu d squared minus 2dx plus x squared plus y squared. This is mu d squared minus 2d mu x plus mu x squared plus mu y squared. Okay, let's bring these to this side, and we can include them into the coefficients here. Okay, bring them into here. I get mu d squared minus 2d mu x plus mu minus 1. It's not a nice looking mu, so let's improve that. Mu minus 1 x squared plus mu minus 1 y squared is 0. Yeah, okay, so this x squared went in here and get me mu minus 1. Same with the y squared. Let's divide everything by mu minus 1. We'll get something really beautiful. Mu over mu minus 1 d squared minus 2d mu over mu minus 1 x plus x squared plus y squared is 0. Now this factor phi, mu over mu minus 1. This is another dimensionless factor. The dimensions of mu is 1, and the dimensions of phi is also 1, are also 1. So I can write my equation like so. 2d phi x plus x squared plus y squared is 0. Again, have you ever seen something so beautiful? There you go. Okay. Everything of this problem has been reduced to this formula, and we just have to prove that this is a circle. And how are we going to do that? Well, by completing the square. Okay, complete the square. So let me go up here and make some room, and I'm going to show you how to complete the square. and then to prove that this is a circle, and then to do some geometry calculations with it. All right, phi d squared minus 2d phi x plus x squared plus y squared is 0. Yeah, this thing is not square, so let's get rid of it, bring it to the other side. Minus 2d phi x plus x squared plus y squared is minus, let's put that a little bit here, like that. Now, let's add a square term, phi squared d squared. That's a square. This is a square, not this. Okay, we have to do it to both sides, though. Phi squared d squared. Now I can factor this into a square. X minus phi d, all squared plus y squared. Let's make this look nice. Take this out. Phi minus 1. There is the equation of our problem. The complete solution is here. This is a circle of radius d times square root phi minus 1. I take the square root of this, I get this. That's my radius, okay? And the center is at this phi d, x, and y is 0. So I compare this to a standard equation of a circle. Squared plus y minus y 0 squared is big R squared. Compare. And we've got it. Center and radius. Incredible. Very, very beautiful formula. It's striking. I mean, the way it all works out into this beautiful thing. The expression for the radius is beautiful. Everything beautiful when you use this dimensionless number phi. Okay, let's try to draw the whole show. What's really going on here? Here's Earth, and here is my origin, and here is Moon. Right. Okay. Now, from Earth to Moon, the distance is d. Okay. D, and it's approximately 384,400 kilometers. That's the average distance, okay, to the Moon. You can use other values if you want. I don't think it matters. The circle will change if you use a different value, of course. But that's the way the motion of the Moon is. It's a little bit closer sometimes, a little bit farther. All right, so from here to here, that's d. Now, what is phi? Phi is mu over mu minus 1, and mu is 81.6. So if you calculate phi becomes 1.0124. That's phi. So phi is a little bit farther than the Moon. You know, phi d is a little bit farther. So I have to go over here. From here to here, this is phi d. This is where the center of my circle of attraction is. All right, let's make this a little bit longer. And now, let's draw the circle. It's hard to draw a perfect circle, but I'm going to try. Okay, that's not too bad. Okay, how's that? It's not good. Hang on. Okay, it's bad. It's pretty bad. All right, let's try again. I have to keep in mind, you know, that the center is here, not on the Moon. Okay, that's a bit better. Okay, there we go. That's a bit better. So the center is at phi d from here. What about the radius? Well, radius, we have it here, circle radius. Circle radius is d squared times d times root phi minus 1. So if you do this calculation, you get approximately 0.112 d. All right. So let's fill that in, 0.112d. It's about 10% of the distance from Earth to Moon. Okay, great. Now, I want to figure out some other things. First thing I want to do is compute, well, actually, this is what you're going to do. You're going to find this. So your problem, your homework, is to find the distance between the Moon and the center of the circle of attraction. Okay, so find this distance. Okay, find this distance. You tell me what it is, okay? Send me a message. Tell me what it is. Use basic geometry. Try to find that distance. What I'm going to do now, though, is I'm going to calculate the classic questions, which are you find this point of attraction where the force is 0, and here this other point where the two forces are equal. Find x1 and x2. So that's what we're going to do now. Find x1, x2. All right, let's take the equation of the circle here. X minus phi d squared plus y squared is d squared phi minus 1. Now, on this line, y equals 0, right? So let's put y as 0 in here. I have x minus phi d squared is d squared phi minus 1. Take the root of both sides. X minus phi d is d square root phi minus 1. And now I have x1. Well, this is two values plus or minus d. So I have x1, smaller 1, phi d minus d root phi minus 1. And x2, phi d plus d root phi minus 1. Now, let's look at the dimension. The dimension of this is length. Dimension of this is dimensionless. This is 1, and this is length. This is length, and this factor here is dimensionless. It has dimension 1. So everything on the left and right have dimension length. So we're okay. Beautiful solutions. If we plug in all the numbers, we get x1 is just about 0.9d, and x2 is farther away, of course, on the other side. It's 1.124d. There. We found those points of attraction. These are the classic points of attraction. Of course, any point along this circle of attraction is a point of attraction. And of course, it's not really just a circle of attraction. It is a sphere of attraction when you take into account the symmetry of the problem. It is a sphere of attraction points around the moon. Something else, aside from this problem, that you can contemplate for homework is to give me some physical reason as to why the center cannot be at the moon. That's an interesting question. It's kind of easy question, but it's interesting to think about, because the first time people see this problem, it's a bit counterintuitive for them to draw a circle that's not centered on the moon. That's an interesting aspect of this problem. Okay, this is a great problem. I really liked it. The way geometry, astronomy, and physics all came together to do this amazing show. All right? And I hope to do more problems like this soon.